Hello. Okay, yeah. Lots of background noise. Okay. Jesse said he might be a little late. He's obviously at his WeRobot meeting. I know he's been posting pictures in the Slack, and I give some pictures that he put up on social media in Slack, and I'll show them later. He comes by, he can tell you a little bit about what was going on there. Looks like that was successful, though. Looks like he did a pretty good job. He had a good time, and yeah, so that happened this week. We also did our meeting for Cognition Futures, which is productive, very productive. And we've been working on some open source things. And maybe I'll talk a little bit about that as well. So that's good. Hello, Morgan. Are you there? I don't know if Morgan's there right now.
Just setting up.
Oh, okay, setting up. All right. All right. So, Amanda, did you have any updates or?
I don't really have any updates.
Okay, that's good.
The Cognition Futures group was good as usual. And also, as usual, I didn't write as much as I wanted to.
Oh, yeah, it's always a problem. Yeah, well, good. All right. So I'll give maybe a few updates here. So again, I don't know if Jesse is going to make the meeting today, or at least the first hour. I'll share my screen and go over some things. Then maybe Morgan can give an update a little bit later. So the first thing I mentioned, of course, is that Jesse has been at WeRobot, which is a conference that he is attending in person in Seattle. And you can see my screen share here, I assume. So let's see, where do I want to start? So this is a shot of this was at Bill Gates Hall, I guess, at the University of Washington in Seattle. And this is the Tech Policy Lab. I think they're sponsoring this, or one of the sponsors of this conference. This is a session here. This is Ryan Callow, I believe. That's the person organizing it. And this is the sort of the setup. So this is WeRobot 2022. And what I understand, it was a lot of technology policy, a lot of work on different things like robots, human-computer interaction, things like that. So it was a pretty diverse group of people there. This is some demo that was ongoing there. I don't remember the details of it, but Jesse mentioned what it was, and we'll have to ask him when he comes into the meeting. This is the Big Dog robot. This is a Boston Robotics bio-inspired robot. It's inspired by a dog, and it's meant, originally they got a lot of their funding from the military, so it's meant to be like a robo-soldier or something, but what they've been able to do is build a robot that can ambulate much like a dog or a quadruped of some type. I think that was one of the big attractions of the conference, was this Big Dog robot. And just, you can see that it's pretty good at quadrupedal movement. And what's interesting is if you put these on rocks or something, it can find its balance, and it can go pretty, it can ambulate pretty well through rough terrain or things like that. So that's why they're interested in this sort of quadrupedic movement. Okay. This is the session here where they have WeRobot. This looks like it's a little bit more packed. And then this is one of the panels that they had, and maybe Jesse can tell us a little bit about that later. This is again that demo. Here's Jesse. Here he is. He's at the University of Washington. Proof he was there. And then this is a session outdoors with the big dog robot. This is a view from the side. And then this is a poster. And this is our poster. This is one of the posters that Jesse created and printed out. So we've been talking about this for a while. This is, I think this is the Our Virtual Lives Digital Companionship poster. So this is, I think, the one with the shared interfaces. That was the internal name for it. And it looks like it looks like it came out pretty nicely on paper. Sometimes, posters are, you design them in whatever program you like to use, and then you have to print it out on this huge piece of paper. And sometimes you can even do it on cloth. I've done it on cloth, and it comes out, and sometimes it doesn't come out as nicely as you'd like. This looks like it came out in a pretty good way. So this is the poster. People had a lot of interest in it, and Jesse's there talking about it, going through the poster. So that's good. As I understand, there was a lot of interest in the poster. So I know one of the posters, anyways. So that's good. That was WeRobot. Okay. So I guess Morgan's ready now, or?
Hi there.
Okay. So you want to give an update?
Well, not a lot of updates this week. We've been doing the in-person meetup. Excuse me, it is still early. In-person meetup at Noisebridge, and hybrid event. So still doing Neurotech events, and I thought again, this is more neuroimaging than say neurodevelopment, but really interesting to see a stable diffusion MRI model. So I posted that in data sci ML. If it's taking everything else by storm, I think it's going to be really interesting to see how it's applied in MR. But it was a good reminder to plug the Hugging Faces service. If you haven't checked it out, Hugging Face has some basically offers a service to run models and play with data sets and I forget what they call it now, spaces. But the group in London also released large data sets via academic torrents. And I think the paper looks like it's really worth going through. This week it was you were at the SIAM conference, right? Yeah. I mean, so in addition, of course, neuroinformatics, the assembly was taking place.
Yeah.
And then in Zurich, the computational psychiatry course started, which even they were doing it hybrid this time, albeit 9 hours ahead.
Yeah.
But again, for anybody interested, they have all their course materials online, and it's an annual. I always use it as an annual reading list. See how their reading list is updated. But it's a awesome group of speakers, and So I've only just gotten my breakfast here, so I will check Slack and probably have some more updates.
Oh yeah, no problem. What was that again? The session that you were talking about,
The computational psychiatry course.
Oh, okay. Oh, that's it. Yeah,
Yeah.
computational.
Yeah. It's an annual event in Zurich that that just is like an incredible set of speakers. You know, it's I mean, in addition, it does try and be a course for grad students and postdocs, but like Neuromatch, you know, it's also got this awesome speaker list. So it's a great way to see kind of, you know, current research, or, you know, different aspects of computational psych, and as well as like they provide all their educational materials and things like that. And I'm still trying to, you know, Guillaume Dumas started his, I think he's calling it just computational medicine course, and a professor at Mount Sinai is definitely a computational psych. I've asked for the syllabus, syllabi, and yeah, they said we will get these out. But yeah, this course has been going on for years now.
Oh, good.
It's great.
Yeah, that's great. Thank you for that update, Morgan. It's wonderful. Yeah, so as Morgan mentioned, I was doing double duty on two conferences this week. I happened to be at the same time. I didn't plan for that, but I did there was a SIAM conference, which is the Society for Applied Mathematics. It was on networks, and so I attended that, and it was very good because there were a lot. It was a sort of a smaller conference. It wasn't like a international. It was international, but it wasn't like one of these large international conferences, and maybe about 100 people there. And you know, there were a lot of different topics in network science. So they had a lot of good presentations there. I don't have a presentation on it myself. I didn't. It was all virtual. I didn't take any pictures. But you know, it was nice. It was a pretty good session. A lot of interesting work going on in different areas of network science. So there was, you know, there were hyper networks, which I gave a talk on. There are other areas of merging network science and machine learning, which I thought were really interesting. And this was also true a few months ago at NetSci 2022. So they had a lot of stuff on like merging machine learning and neural networks with what they call complex networks, which are the thing that the conference was on. So, you know, you have it was a kind of an interesting mix of things going on there. There were other mathematical topics. As being a applied mathematics conference, there's a lot of focus now on on topology and topological data analysis. So for networks, you know, that's like if you have what they call simplex, which is if you can take a network, take the nodes of a network, join them together, and form some sort of shape. So it's like a triangle or a rectangle or something, and then they use those as sort of motifs to look at the structure of the network. So, you know, if you take a social network, which is, you know, this group or any group that you want to take, and we've talked about the Karate Club graph, which they talked about a couple times. You can look at the structure of how people are connected, and you can get a sense of the shape of that network. And there are a lot of things you can say from that. So those were just a couple examples of things. So that was a nice session. The other session I attended, of course, and I don't know if Morgan was able to make this, but the INCF Assembly, which was where we actually had the poster that was presented at Maine. It talked about the updated version of that. So that actually, there's a video on the YouTube channel where that you know, it's like about a 6 to 7 minute overview of that, and the poster was updated for this session at at INCF. So INCF, of course, is our GSOC sponsor. So I didn't talk anything about GSOC in this, but we did have there were a lot of talks at neuroinformatics about neuroinformatics, And there were people doing neuroimaging. There were people doing other types of neuroscience, and their interest in this group overall. I know we kind of deviate probably from their mission quite a bit in terms of what we do for GSOC, but maybe not. But they do a lot of what they call fair neuroscience. And that means is that when you have do a neuroscience experiment and you collect data, the data has to be, it's expensive to collect. And so if you collect a lot of data, you want to be able to share it with people, you want to publish it, you want to do something with it. So then these fair principles come into play. FAIR stands for findable, accessible, interoperable, and reproducible. And so you have to have all of those things in place for your data to make them FAIR compliant. And the reason you want to do that is so that it's usable again. You can share it. You can make sure if there are errors, you can catch them. You can reuse the data for different things. So this is very much this is something that I've been interested in for years. And I know Morgan is interested in being in the open source space in neuroimaging. And a lot of interesting talks, a lot of the sort of the standard talks on it. But they talked about a lot of different initiatives going on in that area. They also had a tutorial I attended, I think Thursday, on Neuroscience Without Borders, which is, of course, I think Morgan knows what that is. It's an interoperable standard for sharing data. So you have, and this is something they use in OpenWorm a lot, where you have data. It's usually for NWB, it's neurophysiology data, like different types of neural recordings. And so they use this file format. It's a file format exchange. It's a way to sort of pick tools to analyze things. So it's very in the weeds in the sense of what you're doing scientifically. But it's important to have these infrastructures in place. And so it was a very interesting conference. It was all virtual again. It was in Gather Space, which if you've been to Gather Town, you have this little avatar and you wander around the room, and it's very cartoony, but it's like, well, I'm at an important science conference. I'm in it as a little avatar, but put that aside, it worked out pretty well. So, yeah, that was my week, and I did kind of bounce between those two things.
There's a couple Neurodata Without Border events that are coming up
Okay.
that we talked about on Thursday at the Neurotechnics meeting. Allen Institute is hosting things September 28th. I can put if we don't their newsletters. If you go to their events page, their website, it says like no upcoming events, but they've checked their newsletter. There's like 4 events coming up, so they've got a docuthon that's coming up, and I think that could be like next week, and then the 28th, and then another Allen Institute event on the October 4th. These are all open, educational or great. Allen Institute is kind of hosting, so they're a great resource too. I'll put a link for the newsletter.
All right. Thank you. Yeah, I thought that would be interesting, and there are a lot of events. I'd like to see more interaction there. I don't know. I know we bring people into the lab through like GSOC and through mentoring and other things, and that might be another way to come in to the pipeline, especially with respect to like bringing DevaWorm into the fold, because we have a lot of resources there that tie into it. So it might be something to follow up on too. Yeah. So we've been also working. I was also working on tying up GSOC. So we're kind of finishing up that whole thing. I think everyone but Himanshu is finished with their projects. So everyone submitted last week or this last Monday. So I know that Brian and Hussein have submitted, and I met with both of them this week to talk about what's next. So they're both interested in working further on their projects. Hussein's working on the Big Five cybernetic theory and some of the agent-based modeling around that, which actually should be interesting if people are interested in like, ethical behavior or in personality theory or something like that. There are a series of tools that can be used for that. I know we do a lot of work in GSOC, like producing things, and then they tend to, a lot of people approach this as like, some people approach GSOC as like an opportunity to get people to work on a code base, which is fine. And they get people to do pull requests, which is where they submit some code for review and incorporation. But I don't know how much the students get out of that. So my approach is to give them a project and, have them work on it. And the downside of that approach, though, is that we end up with a lot of things sometimes that don't move forward anymore, And so that's a problem, but also an opportunity, because we do have these tools that are there for people to use. And so that's a tool that might be useful to people. Hussein is actually trying to bring this into. He had a problem with getting PyNet logo to work, but I think he's solved some of those problems. So we're actually going to have some PyNet logo in our operability. We're going to have some ability to use it in notebooks. So in a Jupyter notebook. And other things like that. So that should be good for people. And the benefit of that is just that you can open up the notebook directly from GitHub, run it. It's organized into these kernels, which are these little executable boxes of code, and you just run through, and you can annotate things. So you run through, you hit like it's a little arrow, it's a compile, and you can compile it, and then it runs. You run through all of the kernels, and it should give you, like, it allows you to use it and go all the way through analysis and everything. So it's very user-friendly for people who don't want to really dig into the code. But if people want to dig into the code, of course, that's perfectly okay. So, and then Brian, of course, is working on his, there's a class that he has in conjunction with Albany, and we're sponsoring that class. And I think you met Brianna a couple weeks ago. She's part of that group, and it's just a group of, I think, 4 students who are wanting to work on this auditing tool. So it's called the Sustainability Auditing Tool, and they're working on a set of tools for, auditing open source communities. So Brian has a number of models from his GSOC project, and those models are going to be, he wants to be able to have people select models that maybe suit their needs the best. So if I'm working in an open source community where I want to get certain measures of activity, involvement, engagement, I can, pick one of his models, and I have to figure out which one to use. And then I can get my, I can evaluate my community. Now, the idea behind their project is they want to be able to develop sort of the auditability functions of this further. They also want to be able to allow people to pick the best model. And so we're working through that this fall. And also have it hosted on the web. So it's kind of like a portal. So you can just go to this website. It's a portal. You go in, you select a model, you run it, and you have to know, you have to have some criterion to select it. And then you have this nice tool. And it ties in very nicely with this AI ethics area, because AI ethics, of course, is there's a huge focus on auditability. And it's nice because it's not strictly algorithmic. In AI ethics, there's an algorithmic auditability focus where you're auditing an algorithm and you're saying, what is it doing under the hood? which is very important. But in this case, it's more like I want to be able to know if I'm evaluating my community that the thing that's being simulated and measured is, you know, sort of trustworthy, and that I can apply these things to my community without reservation. That, you know, it's like some sort of um, you know, that there might be, like, it might be misinterpreting what I'm trying to do. So I, you know, I want to be able to do something and make it actually worth my time, you know. So yeah, I look forward to seeing the product of that. Definitely it'll be interesting. So that's what we have for GSOC. And then Himanshu is finishing up his work on his project, and that'll of course be nice because he's working on some reinforcement learning tools, and the auditability group wants to incorporate those as well. So do we have any comments or questions?
Sorry, Bradley, do you have a link for the SIAM conference?
Oh, I can put it in the Slack. I don't have it with me, but
Oh.
it's not like hosted by SIAM. It's hosted, I think, by Northwestern University, so it's like kind of off in the.
Okay.
It's kind of an odd link, but yeah.
Yeah, it'd be great to see the speakers and or you know, just to see the more details.
Yeah, definitely. We'll do that. Yeah, so yeah, and there's something in the chat. Okay, that's Jesse. So I might go over some things in the Slack. Actually, we haven't done that in a long time. Let's see. Yeah, I know we're gonna be excited about this. I'll share my screen, and we'll go over it that way. So let's see. I don't know where we've had activity this week. Actually, Jesse put some things in the general channel on WeRobot that we went over that earlier about how this is actually the work of the Methods CogSci project. Actually would impact the explanatory power and clarity for what technical folks. So you saw some examples of them doing like these software demos in the robotics, and how in turn that affects their ability to clearly associate or discuss regulatory and legislative implications. So I guess what Jesse was getting at here was that there's their focus at WeRobot is in like regulation, legal regimes, and legislative implications of things. So, you know, if you have a robot like Big Dog, what laws do we have to have in place so that people don't use it to run amok or, you know, something else. So, or, you know, if you have something like a touch screen, or, you know, like a webcam, you know, what kinds of laws need to be in place to ensure that those things aren't misused. I know we clearly have them out there, and that's one of the problems, is that we don't have the legal regime that's caught up with the technology. So I think that's a really interesting question. And methods in CogSci, you know, maybe Jesse can talk about this a bit later, but there's this, you know, what we do in CogSci, of course, is relevant to this. And I think it's worth thinking about, like, you know, with our methods in CogSci that we're doing, not only the methods that we want to incorporate, but also maybe some of the ways those can be used in the real world. So I think that's a good question, or a good point. And then,
can you hear me if I talk like this?
Yeah, I can hear you.
Okay, I'll be kind of in a, yeah, Morgan knows what I'm talking about. It's I don't really want to talk too much, but I think I can talk, so I'm going to try for it.
Okay.
Yeah, there's a whole, maybe later on, I'll try to do like a whole overview from the conference and stuff.
Yeah.
But in the short term, that first point, and I made 2 posts, 2 like specific messages in the general chat. And the first one is basically saying, the demo was a very toy example of the brittleness of like computer vision models, and how, you know, if you change the angle of the vision, even though as a human being they were getting at how they're trying to explain to like legislators or people who are totally not, you know, versed in anything technical, and making it really clear and simple in these very simple models of, like, if you're looking at a stop sign at like straight on, it's obviously a sign, but if you keep turning the angle or the distance, it's no longer recognizable by the model that you've trained. And they had a physical camera showing it in really simple terms, almost like a toy model in the most useful, simplistic sense. And it was a little bit of a stretch to explain to them what I was doing, but some people got it. And then one of the like undergrads who was kind of manning the station introduced me to their PI, and I think her name is Cindy Grimm from Oregon State, and there's also someone named like Ross someone, and I'll show you more about that later. But we had a little conversation after that too, and I guess the point being for this thing is, it struck me how specificity in some cognitive ways, which is not at all what they were really focusing on. They were focusing on how do we show someone how easy it is, how brittle this model is, this situation is. Like, you know, they were trying to show how easy it is. But for me, it's like, oh yeah, like this is a really interesting bridge into really clearly showing some of the gaps in what does it mean to have a limited computer, I won't say consciousness, but like a robotic intelligence in a limited capacity versus where humans are in that process. It actually kind of made me think a little bit about that. It didn't quite work out, but that speculative idea of the diagram of embodiment, like levels or degrees of embodiment, that we didn't there's a figure which we were thinking about, but it never materialized. And I think in a roundabout way, it was a nice entryway, because a lot of the, difficulty in explaining to legislators or lay people or other people outside of the field of these fields of study has to do with how do you clearly demarcate that a robot, and I'm using my air quotes here, a robot or an AI is indeed not at all human level, is not superhuman. And there's this sort of a lot of talk about the difference to the subjective, and I think it's, the classic examples, like, I'm trusting Google Maps with my entire life by just staring at my phone as I'm hurtling down the street at several miles an hour. And there's that want of security, and we have such a great example of it, that if you're navigating and you have GPS connection and everything, you do it. And it's difficult to kind of introduce to people where that fails and where that is no right, like how easy it is. People think, oh well, if the Google Maps can do this, then surely, But to point out, it's really interesting to point out how, like, you could physically in your own head manipulating. They had you can't see it in this example, because in the picture, if you go back to the picture, can you click on that? Yeah. You can kind of barely see it in the back. You can see the woman in the white shirt.
Yeah. here?
On the table there are these little like figures, and they're like dolls, and one of them was like a stop sign or a wet floor sign, and the thing you put on the floor after it's been mopped or there's a spill. And being able to physically have in your hand the sign, and then a computer vision, an AI that's hooked up to a camera. So you have like the camera in one hand and the toy sign in the other, and you can physically rotate the sign. You can zoom in and zoom out by moving the camera. And it was just it was really interesting in terms of embodiment. And I mentioned that a little bit, but some folks didn't get it. But if you look at the foreground, and the main subject of this picture, you can see Ross on the right, who's explaining to my fellow at the table here, when we're looking at the iPad or the tablet, and the tablet is basically showing how, from the perspective of a computer vision, a robot, it's attempting to show how, because of its extremely narrow field of view and where the sensors are and where the actual camera is located and the angle it is on the robot, things that are in reality that have sort of congruent shapes within a very limited field of vision will in fact be totally different locations on the same map. Just because if you're in this hallway and you see two black walls on both sides, you could be in the hallway on the left, or there's also one on the right that's slightly out of picture. And then they put like these objects that were like gurneys or other, talking about how sensitive the vision in high fidelity, or how much differentiation you'd have to understand like very small changes in the environment. And so it was a really
Yeah, it was interesting.
nice
Yeah.
toy model. Was that?
Oh, I think that's, you're definitely hitting on something here with embodiment and like image processing and training models and things like that.
Yeah, it was their whole attempt was simply just, how do we show this in the simplest way? And I'm like, that's cool, but and taking it a few more steps and thinking about our methodology project and thinking about even like regulatory implications down the road, it's like the more specificity we can say at it's not as easy as saying, oh well, this robot only has this quantifiable amount of intelligence that's equivalent to a human being at this age. That sounds like a terrible thing to do. I don't want to do that. But like having some gradation that's visible and explainable, and with more, I think in time there could be a bit more refined capacity by saying, here's sort of the spectrum, and here's where things are within that spectrum. And some of the methods, some of the specific hard detail and paradigmatic work may eventually tie into how things are regulated down the road. So that's kind of a long-winded introduction for that. But there's a lot more to say in a more refined way later.
Okay.
There's more I might say about the conference as a whole, but I guess the next thing in there I would just say is the poster session went really well. I was honestly a bit intimidated after the opening. Like the poster sessions was in the afternoon.
Yeah.
And it looks. Someone said, "Oh, look, you're really educating the youth of the future." When I saw this picture, and I'm like, "Yeah, there's like 3 like undergrads here," but I mean, this picture's a little bit deceptive because this hallway was packed.
Yeah.
There was a lot of people that were like all manner of beings were coming by here, and it wasn't just undergrads fascinated with these posters. But I was a little bit intimidated in the morning because one thing was quite useful about Humans in the Loop, which is a paper I'll mention later. And then the next was a really in-depth dive on a very the whole conference was set up about looking at people's papers, and some were very complete, some were not, and like the second panel of the day was just a deep dive into an incomplete law paper, and I'm like, oh man, like I don't really mention law very much in any of what I'm doing. Like it's there, but I'm like, this might feel really out of place now, and you know, so I was kind of bracing for like this might be a hard sell, and maybe I'll stay around for 10 minutes, but nobody's gonna come by, and then I'm just, I'm gonna get lunch or whatever. And I underestimated quite a bit, but I'll go into this more later, but suffice to say, the whole hour, there was like an hour given aside for the poster stuff, and it was kind of blended with lunch and other things. And I didn't really have any opportunity to not talk, because there was like a queue for one poster, and then I talk, and then a queue for another, and this is a lot of people. So it went really, really, really well. I didn't get a whole lot of feedback, but I got what I did in some ways. I had a few people. I think the second individual from the left may reach out to us about joining the lab.
Okay.
She was quite interested. And in that, and saw me out later to talk about that. I don't know if she will now or like later on because of school stuff, but she's very interested actually. And I had a talk with a game development person who was very interested in gamifying. It was kind of like similar what they're trying to do with Plot Twisters, which is about making like a virtual game world eventually. But he was very interested. He worked on, I think he's actually like someone very involved in like the Halo series.
Oh, okay.
And he stopped by a couple of times. He's a very interesting fellow. His name was Mel Cafe. I don't know if you've ever heard of him. But,
no.
Yeah. So it was very interesting in that sense. And I talked a little bit to Ryan also, Ryan Callow, who's the main guy of the conference. And he pointed to a lot of the things that were coming up the next day, because there was quite a bit that was relevant on the second day of the conference, which is true. But suffice to say, for now, I'll say WeRobot as a whole was extremely impressive. Like the Kate Darling one, I posted a few links here. I put to some of those things in Notion. There was also an amazing conversation with if you go all the way down. Oh, I might actually be here. I may talk more about WeRobot in a more full length later on, I guess.
Yeah.
But the last thing I want to mention, there were two smaller points I want to say. One of them is that there was a great discussion, actually. I'll share my screen for a second.
All right.
Because I posted this somewhat on Twitter. is. Also, on a bit of a side note, the MIT AI Ethics Reading Group is starting up again. And I mentioned some stuff at WeRobot, so that'll be exciting. Oh, here it is. Okay, sorry. All right. So I'm basically on Twitter, and there are a lot of good stuff. But I guess what I'll quickly say is this is a really interesting phrase about taking a lot of ethical tech and dealing with the aftermarket, and that was by Tim. I think it was the person who liked this. Tim O'Brien, I believe, said that, which is kind of funny. I didn't know who he was on Twitter, but he was at the conference, and so I didn't tag him because I didn't know if he was on Twitter or not. But anyway, this is kind of the main point that I want to make about the conference, in that it was a really good. It was a really good environment, much better than I expected in terms of interdisciplinary stuff, and being really, really, really constructive about unlike, I've never been to a conference where people have dived so deeply into some of the technical merits of things, and really, really gone deeply into this is a paper focused conference. But it was done collectively. Like you had people come in from like really strong philosophy and law backgrounds come and say, well, you need to tighten up your language here because you're going to be really misinterpreted. Yeah. But it's extremely constructive. And I don't think I've really seen that in a conference where there's been interdisciplinary, in-depth, critical steel manning, and the stuff. But I just the collegiality and the camaraderie and kind of the shared sense of like, the better we do about making these papers, these efforts more aligned, like either even making it better, talking to legislators, talking to the FTC or whatever, like the better things are going to be. Like it's just a real holistic sense of how hard the work is. So I was really impressed by that. I think Princeton and Vision, I'll kind of unfortunately like sarcastically say RIP, as in like, I don't know if that's coming back to the way it was when I was attending it years ago. Yeah. Princeton was an amazing conference in the same spirit, but I don't know if it exists. So WeRobot has kind of been like, oh wow, like it's really there. And Kate Darling, who's a MIT and a very versed person, she said this. She said, "We come together to make each other work better, and it was the best part of it." But yeah, and I was impressed by that. I really didn't know that was part of WeRobot, but I'm glad it is. Yeah. And the last thing I'll say is there was a talk on race and AI explicitly, but it ended up being partially canceled. And so in the meantime, they basically had Chris Dancy, who's a great lab name called Thick Lab, which is like the human in computation and cognition or something like that. But it's cognitive science and AI, and I'm really curious to talk more about it. He's looking at a lot of this like structural stuff. And Tim Brown, who I think is bioethics, and I think he's the philosophy person. And but these two had an amazing discussion I forget where, but like there was talk about epistemic humility, and talk about relationships within bridging epistemic humility, and just many good things. I mentioned we've talked about here before, but like the MIT Tech Review's AI colonialism. Kristen Thomason was a really interesting speaker. She spoke a lot and commented on there. You could have had these like really deep in the field people who are like stars in technology or whatever, and then interspersed with a lot of other, like you'd have people at really high levels comment on work in progress papers, and the sense of community around that was just really impressive to me. So there's a lot more to say, but like as per my general interview, this is the start of the conversation with those two I mentioned before, Tim and Chris. These two. But yeah, there's the whole like there's like the whole second half of the day that I haven't talked about or posted anything about. But suffice to say, I was really impressed, and I kind of mentioned to Bradley I sent him a private message afterwards saying something to the effect of the level of discussion. I'm not going to be a law person, and lawyers can be very articulate when they're at their best, and that's God bless. But the level of discussion and the way in which things were modeled was impressive, and also the sense of like, to be able to push certain conversations forward, you have to be able to be at a certain level of familiarity and technical skill and everything else. And it was really motivating in a way that I didn't expect. So I feel like it sort of set the bar in a certain way, or maybe know where the bar is relative to where I'm at. And it wasn't, I say this because there are many situations like this could be, sometimes you feel that when you're around really harsh critique or much more harsh environments, and this was not. So I'm kind of, I feel like I have a lot to process in terms of, I think it was really important for me in the sense of sometimes some of the big problems that we're working on or interested in seem very far away from reality to anything that matters now. One last point that I have to make that was extremely kind of relevant to this point in a supportive way that's a little bit different. There was one person in the conference. We hear probably when anyone in this lab hears the term AI safety, I would imagine, at least I know, I'm sure Morgan and maybe Bradley, maybe Amanda too, but like, we think of the long-termers, like the rational crowd, the people who are like, AGI is AI safety. We have to figure out AGI, and we know that there's some folks in that crowd who are like, I want to see how people are reacting to this. We know that there are people who are saying like, it's BS if you're not working on AI safety, because all that matters is getting AI as great as it can be, and it's going to solve all of our problems. I'm being a bit manny about this, but yeah, the sense of like, you need to just work on making AI as great as it can be towards the long-term view of it, and deal with some of the technical aspects of that, and don't focus on some of these smaller details because they just don't matter. I'm being a bit unfair to the view, but it was quite interesting because in the context of people doing real safety and regulatory work and security work right now, there's also an interesting group of people from like Germany and that when a Canadian perspective, but some really important folks from like working on GDPR stuff and working in the EU. There's a really nice contingent of folks from giving perspective, like culturally and legally and technically from a non-American viewpoint, which is can be refreshing and interesting at times to say. But specifically, one of them was saying about the here. Yeah, I don't. This is related to it, but one of my favorite moments at the conference was basically someone who was a lawyer person working on real AI safety right now, kind of being alarmed and like, what the hell? Like, there's this group of people that only think about it from existential long-term point of view, and was like realizing, like, questioning. I don't think I've ever met somebody on the other side of it who's coming from a law perspective, and then was like, oh, there's another viewpoint altogether.
Yeah.
So, and being exasperated by that, and being like, how can this be? Because usually it's the other way around. Like, so that was to my previous main point and my last point for the time being. The quality of the discussion and the substance of what people are doing now and the hard work people are doing now in a lot of these areas that we talk about was refreshing and really illuminating what kind of discussion you can have and how it makes real impact now for what people are trying to work with, like these technologies and kind of the power structures behind them too. So I'll leave it at that. I know it's a bit of a soapbox, but
That's fine.
that's kind of my main takeaway
Yeah.
at first glance.
Yeah. Well, thank you for that overview. That was great. You know, it's like hard to capture all that stuff that you've been exposed to into a box, and but I think there are a lot of themes that we've talked about in our group that are. It's interesting how they interface, and conferences are always a great opportunity to kind of get a handle on some of those things. You go back to things that you've talked about in the past, and there's always things you put a pin in and you want to explore. And I know I find that, like, when I go to a conference, a lot of times I do that, and then sometimes I forget about it, or there's a conversation that kind of gets like doesn't follow through to anything else. And yeah, I like that you have this notion. So we have the WeRobot notion. If people want to, it's in the Slack channel. If you want to look through, and we've done this before with other conferences where we have these shared note documents. So go through this, and you can take a look, and if you have a perspective, you can kind of take from that, and then see where that fits into your work. So
Yeah, and two things about that. One, the notion is totally incomplete because I want to put the names in some of the papers in there. The papers that I put in there will kind of be maybe just the titles, because many of the papers are not to be released publicly yet. Some probably never, but so that's why I didn't really. I could show you the program, but like, there's not much I could show. Otherwise, there were no slides in the conference, which was a little bit disappointing. But like, it was kind of this big like paper jam session. But so there's Notion work to be built out, and that's why I feel like I'll go back to something later, and particularly maybe integrate with some of the ethics reading group at MIT. Secondly, I think I was a lot of the work we're doing in the methods project and some of our bigger stuff even like metabrains and these other like really theory heavy things we're doing, I've kind of seen this as a bit like if we're going to ground this and stuff, other people can talk about, we can kind of talk about it in terms of robotics, which is a little bit, tangible but not, and maybe some things like virtual reality or the technology that helps, assistive technology at a cognitive or a level like that. That's a little more human and concrete and kind of more healthcare, a little more relatable to the everyday human experience. And I think we take from this conference, and I'm actually attempting to I'm going to write up something about this event, but I think this conference really illustrated to me how you can do that in a legislative sense as well. That you can tie some of your work to explanatory things that will it's almost like a way of grounding stuff that I just didn't really expect. And it's weird to say you're going to ground things in law and legislation, which feels so slow and so whatever, but like the functionality of both the philosophy, which is quite because there was like some real philosophical critique about how are you structuring an idea in general, and then the functional philosophy, how are you going to explain this in American legal context, which is a whole like, I'm never going to be that person, but like understanding you can ground is maybe not the right term, but you can tie saliency and importance of clarity and message to that context as well. And it was 2 days of the significance of that approach, which I really hadn't considered. So in a way, I think you get what I'm saying, but that was a really, it made some of the work that we're doing a lot less remote and abstract. And when you're trying to explain to people or get funding, sure, but just like comparing the sort of urgency and relevance of some of the stuff isn't just like, oh, wouldn't it be cool to have this model about like embodied intelligence and subjective, bridging the subjective, because I wasn't pressured about this too much, which I was thankful for. But some folks were like, oh, and the big shared code environments, like why do you care about like the subjective divided or not? Like why do you care about reductionism or not? And we didn't go into it too much because we didn't have time, and it was easier to talk about the technology, the case studies in there. But in the light of the conference and what I was saying, like, oh yeah, like the whole the philosophy and the big issues, I really couched everyone that I spoke to, especially the undergrad who introduced me to their PI. She I was very upfront to say, yeah, cognitive science is kind of a mess, and I'm trying to help with that. I don't want to. I was very careful to say, like, I'm not this sort of renegade cognitive scientist who wants to revolutionize how we talk about machine learning and AI and robots. I was very careful about that. But even with that in mind, there was sort of this sense of understanding that, yeah, like if we do make progress in this area, it won't be as sort of abstract and like pointless as it might seem. So there's a much more refined way to talk about this that I look forward to explaining, but I've had no time to do it.
Yeah.
I'm literally waking up Saturday morning very early relative to here, and I missed my flight from Seattle to Portland. I'm in Portland, and so my flight was delayed a couple hours. I'm sure Morgan has experience with that to some extent, and it was kind of the traffic was terrible. People were saying, "Oh, it's the worst traffic I've ever seen in Seattle," and then the airport like, "Oh, it's the worst." And I don't know how much people were trying to save face or whatever. Like, it was the worst like security line. Seattle's security line setup is a little bizarre. Like, they have this like double back lines and everything. But suffice to say, like, I was kind of looking forward to, I'm just gonna get in my taxi and think about stuff, and I'll get to the airport with plenty of time and write in my journal and reflect on some stuff. And that has not happened in any capacity. So I'm a little bit rambly this morning in journaling here, but there's a lot more to say about all this stuff in terms of specific panels and some of the more specific takeaways for our work. So
Yeah.
I think I'll leave it at that. But that's my I guess that's my full report now for the conference. So here we go.
All right, thank you. Yeah, Morgan.
Excuse me. Sorry, I attended a political fundraiser last night.
Okay.
And was talking about psychiatry, or somebody was asking about what I was working on and things, talking about psychiatry, and then they're like, "Well, what are you excited about?" And I started talking about the organoid work that's going on, and it was really funny because the person who's hosting this, who's a lawyer, was just like, wait, they're growing brains. Like, and his first reaction was, we need to stop this. Like what are they doing? And I was like, this is kind of old. Like, this is 10 years old now.
Yeah.
He's like, why am I only hearing about this now? But I mean, he turns to the candidate and he's just like, we need to stop this now. It's like, maybe, I do wonder sometimes, like, how much of a bubble I'm in, and like how widely are known are a lot of topics, and is there really a good discussion going on of the ethics of them and things like that? Because I will joke that I want to grow Daleks. Which luckily he didn't get the reference. Lawyers don't watch Doctor Who, I guess. But yeah, that should scare him. That should scare him. Like, it's designed to sort of scare him.
Yeah.
But that's really interesting. I'd love to, whether or not I can catch the AI and ethics reading group. I'd love to see what they are reading when they start back up.
Actually, let me check now. I'm curious too, because like Kate Darling was sort of the highlight of the second morning. There's a lot of highlights, but I imagine we'll be talking about her. I think she was in one of the meetings last semester. But yeah, I'll know in a few weeks.
Yeah.
Hopefully.
I still, I said this last night, not fully joking, but I was just like, the reason that the roboticists are working on this sooner is that they're afraid that the robots will turn on them. Like, we're not so worried about tissue cultures.
Yeah.
But like you said, Bradley, these are robots that have military applications, and and we're not really that far from it in terms of autonomous flying and autonomous sailing. So yeah,
that's a very interesting comment about how in terms of robots like this, there's really no the market incentives, if you will, for robots tend to either be industrial or military. And so we talk about these like police robots. It's like, well, we're going to repurpose this other robot. And there's a lot of recent discussion about that. So,
Yeah.
Yeah. And I get the thing about, you know, what roboticists are doing is because these are that. And there's a lot of interesting discussion about what, like, where does user responsibility end versus like the pressure to put things on the user and not on the designer and so on and so forth. But you know, if it comes to it, there could be a much deeper dive on many of the different sessions. But yeah, I'll stay vague for now.
All right. That's great.
No, it's cool. The in terms of the robot human interaction, at least in for industrial, there's the professor actually leads the MOAB project at NeurTechX. It's the mother of all BCI benchmarks. I actually works on this kind of robot human interaction. You know, and again, more you know, like you said, it's like industrial robotics is the growth, or you know, is driving a lot of the commercialization, is getting a lot of the funding, and so there's some really interesting work in how to, you know, like we've talked about before about alignment, you know, AI alignment, and as well as you know, how to how to have them working in close proximity. That hopefully will be a really fruitful area for getting at some of these issues, because you know the industrial robotics groups are still very public and still talk a lot about, you know, open source, and but we don't hear anything in the Bay Area about, you know, military robotics.
Oh yeah.
For obvious reasons.
Yeah. Amanda, did you want to add anything? Okay.
Yeah, that sounds very interesting, though. I'm glad that you wrote stuff down in the Notion as reference.
Yeah.
Yeah. I think the challenge will be to put some more specifics there, and then I'm debating about the most tenable way to make something that's more like, I don't know if I want to really do a blog post recap, or like a blog post that's more not opinionated, but like there's sort of this fine line between. I think there could be. I would like to make some kind of an artifact of, here's stuff from the conference that was important for the lab, and I think that might be different from, here's a piece of writing about the event that I would like other people to know about, and I don't know what I want to do about that, but both will be useful. It's just I have yet to fully figure out what I want those two things to be.
Yeah.
But I may reach out to you or others, like in the reading group, the ethics team. Someone there reminded me extremely of a friend, Erin. Like, it was basically Erin if she went into, like if she went in down the grad school road and became a PhD in like technology, data privacy stuff. So I'm really curious to get her feedback about some things. But yeah, there's certain things that have been done. So anyway, we can move on to another topic.
Okay. Well, that's good. Yeah, let's keep talking about some of these issues. They're great. Yeah, and so we have the WeRobot channel in the Slack, and if you want to look through that, that's great. I would definitely recommend it. And then we have some other things in the Slack, of course. We haven't talked about brain organoids in a while. So brain organoids, there's been a lot of activity. Morgan's put a lot of things in the channel. We've done a lot of, actually, so there have been a lot of papers that have come out on different reviews and different studies on different parts of the work, like growing brains or whatever. I mean, if you take this and you talk to someone in another area of life about this, it's kind of like maybe it seems fantastical, but this is a good opportunity to kind of go through a lot of these studies and how they kind of interface into the real world. So, people are working on longevity, they're working on different types of regenerative medicine. They're working on, this is a paper on current progress in understanding schizophrenia using genomics and pluripotent stem cells. So, there's an interest in using pluripotent stem cells as well as organoids for this work. And pluripotent stem cells have been around for about 10 or more years now. It's actually been about 15 years almost. So this is another technology that's evolving in parallel with the organoid technology. And then, of course, being able to do things like reverse engineering the human brain, which is a pretty broad goal, but that's another thing that people are trying to do. So they want to grow organoids and build things like brain assembloids. So, these are things that are building up to a whole brain. You have these building blocks, you have these reprogrammable cells, these pluripotent stem cells, you have things that are approximating different tissues and how cells interact in those tissues. And then you have these assembloids, which are have something to form the ability to form circuits. So assembloids are self-organizing clumps of neural tissue derived from stem cells that have been shown the ability to form circuits. So if we have those circuits in place, then that's another step towards simulating the brain. And this is where we get into this land of people, bioethics has actually been pretty robust over the course of a lot of the time, as opposed to a lot of AI technology. Bioethics was, kind of doing things before we had the capacity to do them. Nevertheless, a lot of legislation is still way behind on some of this stuff. So, it's either they ban things or they don't know what's going on. So it's it's an area that if you're interested in that area, there's some, there's a lot of work to be done in that. And so, yeah, we have some nice papers. There's a single cell transcriptomic profiling of human brain organoids paper. So, we can measure things like gene expression in these cells and these organoids. So, the cells forming tissues, and it can tell us things about what's going on in them. How do they develop? How do what are the vulnerabilities in cells that might lead to diseases, things like that. And then, characterizing these cells is very important. So you have things where, you can build these sort of proof of concept things like synthetic embryos that have a beating heart. And it may not be useful for scientific study, but they're useful to show that you can do something. So there are a lot of studies in this area where they're making these advances and they're sort of proof of concept things. The scientific value is maybe limited, but it shows that you can do it. And that's true of a lot of molecular biology and bioengineering is you build these proof of concept things and you do the experiment and you show it works. And then maybe it's not so reproducible, but you can, at least you can show people how to move forward. So, that's another area that you might want to find out about. Here's a paper on the spatiotemporal dynamics of microglia across the human lifespan. So this is a study about microglia, which are support cells in the brain. And this actually is a nice figure of development where you go from the embryo to adulthood, childhood, infancy, neonatal, preterm. This is in humans. So this is where you get these different profiles of microglia over the lifespan. This is one of these things that they put together through estimates and measurements. So you have this spike in microglial proliferation early in the embryonic period. You have microglial death, which follows little bit different trajectory. And the reason you have these birth and death cycles is because the brain is dynamic, and they may serve some function in development and in childhood. And this is why you see these different things. You have these other processes going on in the brain, of course, like myelination, synaptic pruning, axonal growth, and other things. So this shows you how to put microglia in context. So this is a nice paper to show some of these things and how they work. And this, of course, applies to, like, if you wanted to build a brain or understand, how the biology of our brain works. It's important stuff. So yeah, Morgan's been really doing a lot of nice posting in here on these things, bringing these things to our attention. And then this axolotls work here, which is interesting because in the DevoWorm group a couple weeks ago, I think it was 2 weeks ago, I covered this special issue of Science, which was on axolotls and amphibians more generally. Here's an axolotl here. And axolotls are model organisms. They are especially useful for looking at regeneration, and also their embryos are very large and transparent. So you can see things going on inside of them. And so this axolotl, this issue of Science featured a lot of papers on axolotl and on amphibians more generally, and talking about they were doing a lot of next-gen sequencing, which is where they sequence the genome, but they also look at the gene expression profiles, and you can map those little sequences to draft genomes. So if you have a draft genome of axolotl, which they do, you can map them to different parts of the genome, and you can look at function and structure of development and functional genomics and things like that. But there are a whole host of papers that just recently came out on kind of figuring this stuff out in development, for regeneration and for other types of things. So that was a nice area. If you go back to the recording of DevoWorm for episode 30 in 2022, you'll see what I'm talking about. And then more work on regeneration and wound healing here, and then this cover of Cell Journal where they have this embryo. Did you?
That was just for fun.
Oh, okay, yeah.
Yeah.
Okay.
But that was a terrific issue, and I really want to reconnect with Katerina at UC Santa Cruz and the Brain Engineers group. So I was haven't checked in with them. She might be. I forget where she was in her PhD, but she might be like wrapping up projects now, and would be interested in talking again, and like perhaps like giving a talk about what she's been working on. They had they had a couple of bioarchive papers that presented like we're controlling our electrofluids platform with the Raspberry Pi. Cool, semi-maker projects, but again, like these are connected to organoids, cerebral organoids, bioreactors, which is awesome.
Yeah.
And again, like this particular Brain Engineers group, like this is that's their focus. But they've been very open about their work. I mean, in terms of sharing not only their results, but their hardware, their technology behind it. And I just wanted to say that, some of those links are just trying to also get at how the organoids and pluripotent stem cells are intersecting with the real revolution in multi-omics, that's going on, because it's not only it's like we're able to kind of grow new things, again, which requires, you know, a very sophisticated protocol of, you know, growth factors and bioreactors. But there's this new, you know, there's all these new sec tools. You know, what was the stereo sec?
Yeah,
You know, was the last we covered a couple of weeks ago.
yeah,
I think,
yeah,
even one. You know, there's like a new sec every every week. You know, I mean, we could probably just cover like nature methods, you know, every week, and you'd be seeing some intersection of technology with biology that is opening up a kind of a new facet into, you know, into the complex world there.
right.
That it's really fascinating, and the TED Talk is you know, is what you'd expect is a TED Talk.
Yeah.
But it's, you know, it's a super overview of his, you know, the Stanford group's vision there. It's anyway, lots to follow, and it's incredible science.
Yeah, definitely. Don't let the technical details intimidate you. I know those papers can be incredibly technically dense, and even if you have a background in biology, you can still be like mystified by what they're doing, because they usually present it. They present the whole thing. They don't like. They tend not to be like. They tend to be inscrutable in a lot of ways, especially with like presenting next gen sequencing. I don't think we've quite gotten to the point where we know exactly, like, it's hard to map those results to like something very tangible in the biology. It's just kind of like they'll usually show like a dimensionality reduction map and say these things go together. Other than that,
it is. I mean, I was trying to get this across, was that how much these results are kind of speculative, or you know, like I'm like, you know, trying to get across how you definitely want a pretty deep understanding of ML just to realize how much is being kind of thrown away, or how much is this? These are statistical maps,
right.
You know, we're like, they're kind of recordings. They're based on measurements, but then they've had a lot of other steps have been applied, and you know, and again, like Madeline Lancaster talking about how, you know, even some of her preps are not reproducible, or I don't want to say that. Yeah, that there's definitely a reproducibility problem in organoid work. And sorry.
Yeah, that's true of most a lot of biology, where you have like protocols. Like in a protocol, you usually have a series of chemical reactions that you're trying to induce.
Right.
So, you know, that in and of itself is hard to get to work right. Like you have things with the water quality, the reagents, and then getting that to work every time. It's very hard. But, you know, people have tips and tricks, and it's not, you know, we think of science as being this assembly line, and then especially in molecular biology, even though they do have like, you know, bioengineering, it's not the case that you can always get the correct answer or the same answer. So it's definitely a challenge.
I do think that the artificial embryo work, I mean, it's like it's going to go in parallel with the assembloid stuff, in that like it should be. I mean, it is giving us something that's, you know, I was trying to get across last night that like this is organ generation, right? Whereas we've been doing, or you know, what they've been describing has been tissue generation, right? And so now there's still going to be a group of people who are going to try and take a stem cell and see if they can still grow a brain.
Yeah.
You know, by that I mean an organ, right? And figure out like how we need to do this, and how the you know, how does the matrix need to you know, be different for the scaffold, and you know, and for vascular growth and all of these things. Like they're going to still be trying to build it up like engineers, but this embryo, it seems really remarkable in that like you can now do just full organ growth. And that was kind of the Cambridge Labs point with this. I think it was like PAC6. Like you could recreate this particular organ change that again is seen naturally, and it looked like the brain that grew from this artificial embryo seemed to have that same defect and same same structure.
Yeah.
It really was they had that as their kind of like their powerful demonstration.
Yeah.
We are doing this, and
yeah. Well, that's great. So yeah, thanks for that. So yeah, it's brain organoids. And just to go through very quickly in the rest of this, we have cognition futures, which is very active. We have data science and ML, which has been, there's been this discussion about like the stable diffusion models and the brain diffusion. This is a link to the Hugging Face. Hugging Face.
The new Fast AI course.
Yeah. Fast AI. So this is good stuff if you're interested in data analysis and some of the stuff that we're doing with AI and different types of machine learning. Then we have Ethics, Society, and Tech. We have, hackathons. Okay, yeah, Morgan's been advertising like the NeuroTechX Global Hackathon coming up. Then in network science, I updated this with this is where I went to this is a screenshot from my computer when I was watching the stuff going on at SIAM, the Network Science Conference hosted by SIAM. So this is just an example from one of the studies where they were looking at crosstalk between signaling pathways in cells. So this is like, there were biology studies, there were like social network studies. There were all a wide range of things going on there. We've got some other articles on network science here. We also have neuroscience networks, which is a subset of network science, which is where they're looking at networks of neurons in the brain. And Morgan posted the Neuroscience Without Borders newsletter here. But we also have studies. This is the computational psychiatry. This is actually a review article on computational psychiatry. There's a study, the Big Mac data set, an open resource combining multi-contrast MRI and microscopy. So, this is relevant to building a neural network from data sources. And we have, I know we have like talked about reusing data sets, but this is a nice opportunity for a group like ours because we don't have that. We don't have a lot of primary data that we generate. So using these type of data sets, that exist out in the world are very useful, I think, to addressing maybe some of the questions that we have. And they're hard, maybe sometimes very hard to sort of get to work in your hands, like to get the data, open and start doing some analysis. But it's worth it. We've done a lot of stuff in DivaWorm, for example, with these secondary data sets and utilizing them to answer questions. So definitely, if you're interested, there are some channels here in terms of data. The data science, ML, neuroscience networks often has stuff in this area. And then even brain organoids may have some things in there. So I think that's enough for the Slack. I know we're already pretty late, and so check out the rest of the channels if you're interested in. So there's always stuff being posted in there. So I want to go on and talk about preparation for NeuroMatch 5. So NeuroMatch 5 is coming up on the 27th and 28th, I think. It's not this coming week, but the next week, and it's like Tuesday and Wednesday or something like that. So that's coming up. We've got to get moving on some of these things. I know that we had the layers, folds, and information processing submission accepted. We had the intelligence offloading submission accepted. We had something on the methods accepted. And then Brian has a submission on some of his stuff with intuitionist math was accepted. And so now the next step is to create a talk, like about 7.5 minutes, I believe. So this is, oh, go ahead.
Is there a specific date that the talks have to be submitted to them? Or is that not?
They provided a link, and then that link promptly went to the like submission deadline for the abstract. So
I'll ask them about that.
yeah, please do.
They're pretty-
But I think like probably a week or so before the conference, but it's easy enough for some of our submissions. So we have the layers and folds one that was actually done for Bika. So there's some modifications for the NeuroMatch version that are being done. But this is the cover. So if you're doing one of these talks, you'll have a cover slide that looks like this for a NeuroMatch. Yeah. So this is the one for layers and folds, and then this is the one for intelligence offloading. And so for both of these, we already have talks. They just need to be modified a little bit for the format of the conference. And then I'll record these actually, and they get submitted as videos, and then I guess during the conference they just get replayed. It's not like NeuroMatch is like that. They have like everything pre-recorded and available on demand, which is good because not everyone can make a certain time. They'll schedule things like at 2 a.m. for someone's time zone, but other people are able to see it in the middle of the day. So it's very convenient that way. But yeah, so this is coming up, and we need to. I don't know, Brian's not here today, but need to remind him that it's coming up. So we have the NeuroMatch channel in the Slack, and that's where we'll be posting a lot of this stuff. And I look forward to it. I don't know if everyone's attending, but if you're not presenting, I would suggest that you could attend. If you don't have, I think you can get the fee waived, so that's fine. And then it's a very intriguing conference. There's a lot of good stuff there. It's very diverse in terms of the talks. So and again, if you go and you have a certain interest area, it's worthwhile maybe sometimes to get outside your comfort zone and go to these other sessions, because they often can be interesting to you in different ways. So yeah. So that's all I'm going to say about that. I think it'll be a nice conference, and I think we have some good stuff this year for this. I was going to talk now about this little story that I'm going to tell about a curious moment in the history of PlayStation devices. And so I don't know if anyone's heard about this, but
I know that story.
Okay, you do, good. So we talked about like how people are getting the stable diffusion model to work on like silicon chip Macs and things like that. So that's been an advance from like the sort of the big computing model of large machine learning models, bringing it down to something that you can use like in your house or in your lab. This is an interesting side note of history because in a lot of scientific fields, such as chemistry or in astrophysics or some other area, people need to use supercomputers to do their computations. So they need to take cores, and especially like 10 or 20 years ago, they would need to take cores and chain them together so they could build a large machine that would do parallel computations. So, a lot of universities have these where they have huge supercomputers. I know the University of Illinois has a couple of these huge supercomputers where you have like thousands of cores and you can put jobs on them and do them very quickly, as opposed to like doing them for running your computer for like 6 or 7 weeks, which is what people have done in the past. It's not efficient, but But sometimes you don't want to because it's expensive to do this. Sometimes you want to build your own thing. So this is what people were doing with PlayStation supercomputers. This is people think of the PlayStation as a video game machine, and they should, but video gaming requires a lot of graphical processing. And so the PlayStation 3 was interesting because it offered that graphical engine you could also use to analyze data and do other computations, but it was also open. Like you had an open architecture for running it, controlling it via some Linux.
Yeah, they allowed you to install Linux.
Yeah. So it says one PlayStation can play a game, but 100 PlayStations can peer into the secrets of the universe. So this talks about PlayStation 3s, which are pretty dated now, but at the time it was a state-of-the-art computing platform. So they had a bunch of these. This is something so those squat boxes hulking on entertainment systems or dust covered in the back of a closet were once coveted by researchers who used the consoles to build supercomputers. With racks of machines, the scientists were suddenly capable of contemplating the physics of black holes, processing drone footage, or winning cryptography contests. All the things you need a lot of computational power before. It only lasted a few years before the tech moved on, becoming smaller and more efficient. So nowadays, we don't necessarily need to do this. We can use other things, but at the time it was a very good computational engine. And so people still use graphical processing units, for example, or GPUs come from this history of using them for processing graphics for video games and for other applications. So this is definitely this history of this type of computing. It has a really rich history.
If I remember right, it was kind of like partly Sony's ability to buy chips at scale like that.
Yeah.
And partly that they were also, like a lot of these manufacturers, they're selling them kind of at a loss, because they make their money in the games.
Yeah.
And then he just realized that it was in this, great spot in terms of price performance, where you're like I should just buy 1,000 of these.
Yeah. So, this is, the idea is that the same power that made it possible to render Shadow of the Colossus and the grim storytelling that was involved in that was also capable of doing massive calculations. So if researchers could configure the machines the right way, they could link them together. And suddenly these consoles or computers started to become far more than the sum of their parts. So this was cluster computing, which is still a thing, but in this case, you're using a bunch of processors to distribute the job and to get it done faster. And so this wasn't unique to PlayStations. Plenty of researchers were trying to harness computers to work as a team. So this was something that was going on in the aughts and in the teens, where they were trying to figure this landscape out. Like I said, they have, a lot of universities have these kind of clusters where you have thousands of processors and you have to distribute the job. It's worth noting that requires some programming innovation. In other words, just throwing your job on a single computer, you don't need any special programming, you just run your program. In these clusters, sometimes you need to write the program so that it balances between the different, balances the job between the different clusters. So there's what they call load balancing and other issues. And, this is a thing that it's a whole field called parallel computing, where they have to write programs that allow you to distribute the job across these different cores and use the resources optimally. So the game consoles entered the supercomputing scene in 2002. So this is 20 years ago, when Sony released a kit called Linux for the PlayStation 2. It made it accessible. They built bridges so that you could write the code and it would work. So this is a stumbling block, of course, where you have this idea, but you don't have the code. If you have the code prepackaged for people, it makes it much easier to use things in a certain way. And so, yeah. So there were different groups, like at NCSA, they had a bunch of PS2s that they used, and they used Linux to tie them together. and they used they said it was something resembling a supercomputer. So they
Sony used to run folding at home.
Oh yeah, yeah.
like you could get a desktop of folding at home, which was an awesome use too. Yeah.
Right. And folding at home, of course, was a protein folding application where you could do like what would happen was you download these. Is a little different way of doing cluster computing.
But I think they were using Boink.
Yeah. So you would download a client, and it would allow this program to use your extra compute cycles to do these computations. So, protein folding is very computationally expensive. But if you distribute this program across 1,000 computers and it uses its spare compute cycles, it uploads the results back to a central server and it puts together the computational result. And it does it a lot faster than actually. I had a story when I was working in the lab about 20 years ago. I was using Boink to do some of this, and the IT people got upset because they thought it was like a virus. And
or Napster.
Yeah. Well, Napster's another example where they have this distributed computing model. But this is the type of thing they were doing back then to really kind of wring every last bit of computational power out of hardware for these problems. And of course, now we know that like with protein folding, you can use deep learning, and of course we can but we have to do this on really large supercomputers that are proprietary. We can also do it in like these clusters. Still, we can do cluster computing, but it's evolved since this time. So basically, eventually, like all good things, this came to an end. Basically, the PlayStation evolved, and they basically had a security breach. Like I mentioned earlier, that the IT people get upset when you do things that are kind of weird like this. So they had a security issue with these PS3s, and the PS4 came out was not as accessible, and so it prevented people from using that hardware to do these. And then by that time, the PlayStation 3 was pretty much out of date, and people moved on to other things. So this is an example of the PS3 supercomputers lined up on a rack. They're all connected, and they're solving these problems. So, if you want to look at like black holes or some other large problem where you need to simulate a lot of things numerically, this was how they would do this. They would line these up, they'd hook them up and run them in parallel. So this was definitely a way, if you had a small budget, that you could do this type of computing. So this is a nice article. It's from The Verge. I can put it in the Slack, but it's definitely a nice overview of that point in history.
There's like a year or so ago, Oracle did a similar thing with Raspberry Pis. So they did 1,024 Raspberry Pis, and the trade-off or the difficulty in the programming is is basically figuring out the latency issues you have for the RAM versus the hard disks versus the interconnects between the boards, right? So like you want to have your kind of like your fastest Ethernet or something like that, so that you can connect the computers together as quickly as possible. So you'll see this in the data centers now. They've got these like very high end interconnects between the boards. Much faster than say gigabit Ethernet or something like that. And this came out when, or we were talking about this with the Neurodesk developer, because he's using Oracle Cloud at the back end. If you use MPI for doing this kind of distributed programming, you get the benefit of this high-speed bus between computers on the Oracle Cloud. And anyway, there's a project, I think it was just a Kickstarter called Turing Pi, that is like it's a simpler. It gives you basically a toy system that you can use to think about the programming issues, right? So it's like a board for like 4 to 8 Raspberry Pi modules, and then you can kind of think about the parallel processing in a realistic way. It's still it scales really well. I'll drop a link to the article because it was a cool. It was really kind of it was a nice art project because but it is useful, and the ARM architecture, which is what Apple's adopted, is really very powerful. When you're not buying a $40 computer.
Yeah.
Like Raspberry Pi. But even the Raspberry Pis together, show the benefits of the parallel processing, and some great computer science that can be done with those systems.
Yeah, Raspberry Pis are a little low powered for like a massive supercomputer, but you could do things that were, especially if you're trying to do things in like in a mobile context where you're out in the world and you want to maybe configure some robots or something.
And you want to say run it from a battery,
right?
Because they're much lower power.
Yeah, that's great. So that's that little historical point. I like to bring these things up because I think it's kind of interesting to see where we've been and maybe things for the future. They're kind of interesting to people. So I'm gonna move on to some papers. Let's see. Oh, Jesse said something. That's a hell of a subtitle. I'll have to repurpose that one. I don't know what the subtitle was, but
it was about one PlayStations for video games, hundreds, like you peer into the mysteries of the universe.
Yeah, that's quite so. Yeah, well, that's what they're trying to do, right? But great. So I'm gonna talk about some papers now. Let's see. So let's see. What do we actually? When we talk about these, so this is something I've been kind of sitting on. We talked about this. We were talking about this, I think, earlier about cultured neurons and how they might attack the world, but they probably won't. But maybe they will, because you can take cultured neurons, as we've talked about, and build these closed loop control systems. So I think we talked several weeks ago about these hybrids, which are these systems where you have like a dish of neurons and you're recording from them and you're stimulating them. So you're stimulating them from some virtual environment or some environmental thing that's going on. And then you're recording their response to that and you're mapping it to maybe some sort of avatar or robot. So you can actually build these kind of, cell cultures that actually have some consequence on the real world. So this is something that we talked about a while back, and I wanted to revisit it because it does have some implications for closed loop control and for brain-machine interfaces and things like that. So I think, let's see, this is the paper here. I think this is something we talked about when we were talking about hybrids that we just kind of glossed over, and we didn't get into it any more deeply than this. But this is a bioengineering work. This is engineered gene circuits capable of reinforcement learning. And this is, of course, the reinforcement learning that we're familiar with from psychology, but also from computational models. And so we're building these engineered gene circuits. They can do this reinforcement learning. And this is something that we can implement in bacteria. So this is something that, in AI, we build with just with a program and we simulate some agent. In this case, they're actually simulating bacteria. They're using these gene circuits to, reinforce what the gene circuit is doing. And in bacteria, a gene circuit will be responsible for producing an enzyme or maybe facilitating some behavior, simple behavior. And so then the bacteria are able to gameplay. And so what does gameplay mean? Well, the abstract reads, the engineering of living cells are able to learn by themselves. So, we can engineer living cells to learn. They don't have brains, but they have these gene circuits. And so the gene circuits are stand-ins for brains out where these, whatever brains are. Because like we've said, we don't really, we assume brains are these things that are, allow you to think or allow you to adaptively behave. So it may be that like you can replace the brain with something else. You could replace it with a circuit made up by genes being expressed, or you could simulate it through some sort of model of mechanical model, even like we saw with the robots that were walking. Those robots. The big dog robot was walking, but it didn't have a brain. It was just generating movement from, by mimicking what a dog does, with the gait and the sort of what they call a passive dynamic motion structure. So those things, are able to replicate these kind of behaviors without a brain. And so in this case, you use living cells and their gene circuits to do this. So they can learn algorithms such as playing board games, a classic challenge for artificial intelligence. So the early AI, they were trying to get machines to learn chess or to learn other things. But this is a nice benchmark for a lot of things, as it turns out. We still use, video games and reinforcement learning benchmarks. So these are good benchmarks. It also allows complex ecosystems and tissues to be chemically reprogrammed to learn complex decisions. So you can actually, these algorithms allow complex systems, chemical systems such as gene circuits to be reprogrammed to learn these decisions. However, current engineered gene circuits encoding decision-making algorithms. So, these gene circuits are like basically where you have, I can use my board here. I can show kind of what it looks like. So a gene circuit is like a series of units, and those are genes, right? And in bacteria, the genes are actually pretty simple. In mammalian cells, for example, they're a lot less simple. But you have these units that are joined together, and the units usually have sort of like a promoter and a coding region. All right. And so this is a bacterial genome. It's going to be a circular thing. So it's like they're arrayed in a circle. There's a start point, and then it goes through and executes in sequence, or it executes. There's certain genes. There's very little slack or junk DNA in the bacterial genome because it's very highly optimized. All right, so it's a circular genome like this. You start here and it terminates here. And all these genes are, these genes can be joined together in circuits. So this is a circuit where these three genes are going to be active at different stages of this process. This promoter region is going to be like an on-off switch. And I'm simplifying this for purposes of demonstration. Okay, so each of these are an on-off switch. And this circuit works by making a binary decision here, saying 0 or 1. You turn it on, you turn it off. And then this gene is expressed. So this is a gene, this is a sequence of DNA that does something. Maybe it produces an enzyme, or it produces something else that's important. And so you can measure the state of this part of the circuit by looking at how much of this enzyme is present or absent. So when it's turned on, you see the enzyme being made, the enzyme is building up, you can measure it. If it's off, the enzyme decays and you get less of it. Now, the other thing about the circuit is that these things are connected. So that means that this is turned on by some decision. Then this gene is connected immediately downstream. And it may not be downstream in the circular genome, it's just part of that circuit. And this enzyme usually is the trigger for this on-off switch. So if this enzyme has a certain threshold of density, if the enzyme is around, or if it's being expressed, if it's detected by this regulatory element, then this will turn on. And in turn, it'll produce something here, another enzyme or some other product. And then the same logic holds for this part of the circuit, where you have an on-off switch. Again, it's binary, and then this is produced. And so this circuit can be manipulated. You can have other components, you can add them in. You know, you can have like things chained together in different ways. And so, you know, if you build a circuit, you know, you can do different things with the circuit. You can build like different, you can produce different types of medicines. You can produce different types of, you know, phenotypes in the bacteria that allow it to do certain things. So these are very useful structures, but you notice the structure of it is that they're connected pieces of sort of binary switches. So it's almost like a computer. And so this is basically a biological computer. So we show a strategy for engineering gene circuits to rewire themselves by reinforcement learning. So this whole structure here is going to rewire itself via reinforcement learning. You're basically trying to figure out the optimal configuration for this gene circuit, and then when the cell culture is stimulated, what's the output? So if you stimulate the cell culture, you want to design these gene circuits within each cell's genome to respond in a certain way. So that's the closed loop aspect of this. We show strategy. All right, so this is where they require supervised tuning. So a lot of these gene circuits, you have to design them by hand or by computer, but you have to be intentional. In this case, what they're trying to do is trying to get reinforcement learning to do the work. We created a scalable general purpose library of Escherichia coli or E. coli. So this is a model organism bacteria, different strains of this, encoding elementary adaptive genetic systems capable of persistently adjusting their relative levels of expression. So again, these genes are expressing things, and you can turn these things on and off to get them to regulate. Now, they don't have to be binary switches. They can be like thermostats. So you can turn them up and down, and you can get a certain level of expression, and they're very tunable in that way. You can also turn them on and off at different times. So there are different ways that this can be done. So this tuning aspect is very important. And then, you know, this is, you're able to adjust the levels of expression according to their previous behavior. So this is this sort of closed loop feedback that we're looking for, and we see in human brains or in other types of brains or in neurons even, which are seeing this in a gene circuit system in a bacteria. Our strains can learn the mastery of 3x3 board games, such as tic-tac-toe, from what they call a tabula rasa state, which is, of course, what we call the blank slate in neuroscience or in cognitive science. But this is basically where that this gene circuit is not designed for any sort of feedback or any sort of function. It's just kind of they're maybe connected, maybe not, and they kind of have random outputs or outputs that don't resemble anything you want. And so this is basically they're able to train these gene circuits to play a 3x3 board game. And so we provide a general genetic mechanism for the autonomous learning of decisions in changeable environments. So this is a really interesting paper. They're using a lot of like bioengineering methods to do this. So it's not just simple as drawing out a circuit on a board. The circuit design involves a lot of like bioengineering here. And, you know, trying to get the thing to play an optimal strategy in this tic-tac-toe game, which is something they did with early computers. So you're following in the footsteps of that type of thing. So I guess they're able to do this somewhat effectively. They call it a non-memregulon co-culture. So this is like a memregulon is like the memristor from bio-inspired computing or biomimetic computing. And then the regulon is actually a term that they use for these gene circuits in bacteria. They call it a regulon. And so that's what they're getting at here, the 9-memregulon co-culture. So this is like where they're getting a whole culture of bacteria. They're synchronizing the output, and they're trying to get it to play this game. So we asked if our experimental algorithm could allow a naive bacterial player to learn mastering the tic-tac-toe game. We chose bacterial cultures to be second player because the naive player had a low starting expertise. The starting co-cultures consisted of the same nine memregulon strains at equal cell ratios and equal weight, so they had to like regulate the number of cells in the culture and do things like that. But basically, they were able to get this to work. And so I don't know if they have any nice pictures here. Discussion. Let's see. So this is the memregulon. This is where they have these fluorescent markers where they can like they can measure the expression of some of these things. They have an inducer, which is the thing that induces the gene to be expressed. They have other things in here. Then they have, this is how they do their cell culture. This is the stability of weights, which is actually like these different these different markers, and they use it as a way to like kind of look at the weights. So this is a kind of an interesting way to look at like neural network weights when you're using these gene circuits. Then so this is a pathfinding thing where they have a rat in a maze and they show the optimal path. And then they show how this works in a binary decision-making way. And then they're just trying to replicate this type of behavior in the cell culture where they have this pathfinding aspect where they're optimizing, rats are optimizing their path of the brain. And they're able to do this with the bacteria. So they have this experimental learning algorithm that they're taking from reinforcement learning, which is derived from rat behavior in psychology, but then they're using it to do this task. And so this is a lot of nice stuff in here. They have positive and negative reinforcement, and they kind of break this down. So I'm not going to go through this paper too much more, just to say that, you can, they have a learning map. They have this all really worked out really well. So if you're interested in this area, take a look at that paper. Then there's this paper, I think we also mentioned this the last time we did this. Cultured cortical neurons can perform blind source separation. So blind source separation is, if you're familiar with independent component analysis, it's a statistical technique. This is something that is done, what they call blind source separation. So you have independent sources that you're trying to separate out in a tangle of signals. So if you had like a bunch of auditory signals that you're hearing all at the same time, you would want to separate out the independent components of that. And they use that in neuroimaging a lot to separate out signals that are convolved in different ways or tangled up in different ways. And so this is a technique that we use statistically, but you can also do this with these cultured cortical neurons. And this is according to the free energy principle. So they talk about the cocktail party effect, which is something actually that comes from auditory neuroscience, where someone's standing in a cocktail party and they're listening to all these different conversations, and they have to like fixate on one conversation and pull the information out of that conversation. But there are a lot of things going on around them, so that really requires the listener to lock onto a conversation and pull that information out and isolate everything else. And so that's what they're trying to do with cultured neurons, is to find different signals and isolate them. So blind source separation is the computation underlying the cocktail party effect. A partygoer can distinguish a particular talker's voice from the ambient noise around them. Early studies indicated that the brain might use blind source separation as a signal processing strategy for sensory perception, and numerous mathematical models have been proposed. So we have good mathematical models for this. But it remains unclear how the neural networks extract particular sources from a complex mixture of inputs. Now, in this paper, they've discovered that neurons in cultures of dissociated rat cortical cells, so this is just a culture dish of rat neurons, they're cortical cells, and they grow them in culture, so they establish connections, but they're on you could say a two-dimensional plate. They're maybe three-dimensional in some way, but it's not really it's not like an organoid, which is what we've talked about with these large tissues that are things that are organized into tissue. So they're just cells that are establishing connections. could learn to represent particular sources while filtering out other signals. Specifically, the distinct classes of neurons in the culture learn to respond to the distinct sources after repeated training stimulation. So these are disembodied in the sense, almost in the sense of the brain in the jar that we know from cognitive science, that they're just kind of establishing connections and there's no reference in terms of a body or in terms of ears or in terms of even spatial inputs. You just give it inputs in different ways and it can do this. Specifically, the distinct classes of neurons in the culture learn to respond to the distinct sources. After repeated training, the neural network structures change to reduce free energy. So there's an energy minimization here, as predicted by the free energy principle. This implicit learning can also be only be explained by some form of Hebbian plasticity. And so this is a technique. This is a method that's been proposed in the neuroscience literature, which is where you have a reinforcement of neural connections by previous neural activity. So these results are the first in vitro as opposed to in silico demonstration of neural networks performing blind source separation, and the first formal demonstration of neuronal self-organization under the free energy principle. So this kind of goes through this study. Here's the cortical culture. This is where it's at 20 millimeters, and this is 200 microns, which is a lot smaller scale. It shows how they're packed into this culture with the stimulator and the recording devices. This is the voltage over time. So this just describes this culture of neural network. And then this is where you have these different sources. So you have two speakers, their speech is overlapping, and then the listener has to pull those apart. And then this maps to some unit activities in the culture where different sources are, the cells are around different sources, and they have to, those signals have to be disentangled. So yeah, this is where we have stimulation pattern generation here. We have a source, we have an input. So we have these experimental, this is the experimental protocol where they're showing this disentanglement of the signal, these different trials. And then this is how the stimulation pattern is common for all trials. And then this is an overview of the experience. So there's a lot of stuff, experimental detail in here. I'll go past that. I don't know if there's a summary slide that shows, or a summary figure that shows this, but this is what they call callback Leibler divergence, and it's an information measure of the sort of the separation of these signals. So this is the change from baseline. This is over trials, and you can see these red dots are separating from the gray dots and the white dots here, which is a way to show that the distinct response sensitivity to different source stimuli. So it's separating out like that. So over time, you can see that they're learning this. And really after about 45 trials is where they really separate out. And so that's shown there. And then this is again population activity in these cultured neural networks where they're showing this distinctness. And then they show the free energy principle, namely how energy is lowered in this type of an environment. So, and then that's that paper, and that's a nice paper to go over if you're interested in cultured neurons doing this. So we've talked about bacteria doing this. And then this final paper is machine learning driven bioelectronics for closed loop control of cells. And so this is a paper on sort of for bioelectronics more generally, talking about machine learning driven approaches for this closed loop control. And so this Michael Levin is on this paper among other people. And so the abstract for this reads, from the simplest unicellular organisms to complex animals, feedback control based on sensing and actuation. So it's that sensing of things and then the control of things through actuation is a staple of self-regulation of biological processes and is a key to life itself. Malfunctioning of this control loop can often lead to disease or death. So this is where this closed loop control is not maintained or it breaks down in some way as maladaptive, as we can say. And when they say often lead to disease or death, this is usually like, if you're in a self-driving car and it goes off the road, ranging from that to like maybe something like homeostasis being maintained in a tissue. So there are many different levels to this closed loop control and how it needs to function properly. Bioelectronic devices that interface electronics with biological systems can be used for sensing and actuation of biological processes and have potential for novel therapeutic applications. Due to the complexity of biological systems and the challenge for affecting their innate self-regulation, closing the loop between sensing and actuation with bioelectronics is difficult to achieve. Herein, bioelectronic proton-conducting devices are integrated with fluorescence sensing, using machine learning to provide closed-loop control of bioelectronic actuation in living cells. So we're going back to mammalian cells now, where we were talking about your bacterial cells. Now we're talking about mammalian cells. So again, these aren't necessarily neurons, but they have the same quality of being able to be involved in a closed-loop control system. Proton-conducting bioelectronic devices control pH in a microfluidic system that houses pluripotent mammalian stem cells. So this is where you have a microfluidic system is just a very small set of channels where you can have cells in a liquid and they move around and you can actually move things around the system. So a microfluidic system is kind of like a circulatory system or like in a tissue where you have a lot of fluids. Cells are embedded in a fluid that's flowing. And so you can mimic some of these flow parameters in the system. And this is actually good for looking at cell motility, but also for exposing cells to sort of naturalistic conditions. And so in this case, you're looking at homeostatic control. You're looking at the control of pH in these sort of analogs of a tissue or a biological system, an in situ biological system. This pH control affects the membrane voltage of the cells, which is, of course, doesn't necessarily have to be related to action potential, but it's just the closing and opening of ion channels. That is measured using genetically encoded fluorescent VMEM reporters. So they're, again, these fluorescent markers that they use to look at the level of voltage. In this fashion, proof of concept real-time control of VMEM towards a desired set point is demonstrated. So they demonstrate this set point control. So you're looking at like a very simple homeostatic system, and they're kind of breaking this apart and showing how closed loop control can contribute to that homeostatic regulation. Given the importance of VMEM in cell function, differentiation, and proliferation, so this is where membrane voltage, which is VMEM, is very important in these different aspects of cells, in stem cells, but also in other types of cells, in their maintenance of their behavior. This proof of concept opens up many possibilities in bioelectric closed-loop control of cell systems. So this is a nice paper that demonstrates that you can have this sort of this machine learning intervention into the system in a microfluidic system. And it shows basically how homeostasis is maintained and achieved in cells. And we're kind of putting in this machine learning aspect to sort of provide an artificial way to sort of understand and sort of enforce that closed loop control in something like a microfluidic device, where you wouldn't necessarily have that type of control of pH. So that's a common problem in cell culture, is maintaining pH. You have to monitor it very closely. And if you're doing something like tissue engineering, doing it in a microfluidic system is more natural than, say, doing it in a cell culture, but it comes at the cost of not being able to control some of these variables. So this actually allows us to control this. And of course, if you're trying to do something like, long-term cell culture for maybe something like transplantation, then this is a valuable thing to have, is to be able to sort of simulate and understand the sort of the homeostatic functions and roles of these, in these systems. So they use this machine learning technique to sort of intervene. And they kind of go through the technical aspects here. They show what a microfluidic device looks like. This is where you have a reservoir with liquid in it, and have things flowing through it, and that's how that works. Yeah, so I think that's good. I think that's good. See, we lost a couple people, but yeah, that's fine.
Really great stuff.
Yeah, I think that's a nice follow up to some of the stuff we were talking about with respect to I can't remember what the conversation was. It was about hybrids, but also about some of these things in tissue engineering and in our our assembloids and organoids.
Yeah. No, I'm looking at some of Selberg's review papers too. The potential for convergence between synthetic biology and bioelectronics is a lot of the kind of stuff that you were covering there.
Yeah.
And again, like microfluidics, so important for these, system on a chip designs.
Yeah.
And how to control those, and but going back to the ICA, just made me remember, at least the original paper for me was the Bell and Sinowski paper from 1995.
Yeah.
And it's how they talk about it as a self-organizing learning algorithm.
Right.
And I know. Well, I've seen people talking about other ways to kind of reformulate PCA and see it as well, but it's actually good to go back and an EEG is where it's been it kind of was first used more than say an fMRI.
Right.
But everybody was using the Infomax algorithm.
Yeah.
And so even better to follow up on that in terms of I'm already back in papers in the 1980s.
Yeah.
and which reminds me of the maximum entropy conferences.
Oh.
It is. It's great to see. When we talk about these neural networks, they're showing that we can have BNNs.
Yeah.
BNNs can compute these blind source separation algorithms, it's a really interesting set of connections. Again, with like going back to old things, but being able to do them in new and interesting biological ways.
Yeah, that's great.
So it seems like another person down in Santa Cruz that I've got to try and connect with.
Yeah. All right. Well, yeah. Thank you, Jesse and Amanda, for attending. Looks like they had a good time and they had to go, but so if we have any interesting follow-ups to this stuff, we can put it in the Slack, and see everyone next week. All right.
Take care, Brad.
Talk to you later.